Okay, YouTube, in this video what we're going to do is we're going to set up the relationship between complex numbers in rectangular form. That is to say, some complex number a plus bi, the relationship between it in rectangular form and it in polar form. And so let's go ahead and take a look at this situation that we have here and then explore these relationships. What we see here is that we've been graphing complex numbers in rectangular form, and that is to say that we had some a and some b that we knew if we went a units to the right, let me switch my colors here, a units to the right and up b units, that we would arrive at this point right here. Now previously, in the past at least, in former units, we've looked at a way of expressing this number instead of being a distance to the right and a distance up, as instead being some angle that we're heading in, some direction that we're heading here, theta, and some distance out from the origin here. And so by looking at this right here, we could at least revisit how we've explored how a and b relate to r and theta in the first place. And so over here on the left, we'd say, according to the definitions of our trig functions, if we want to relate r and theta to a and b, one way we could do it is we could say that the cosine of our angle here in this right triangle, the cosine, remember that would be adjacent over hypotenuse, we would get the cosine of theta is our a over our hypotenuse r here. And trying to relate a to r and theta, one thing we could do here is we could multiply both sides of this by r. And so one thing that we've seen in the past, except with x, we're seeing now with a, we see that a, this x distance here, is the same thing as r cosine of theta. And likewise, if we were to set up our sine relationship here to relate r and theta to our a and our b here that are known, we would say that the sine of this angle would be our opposite over hypotenuse, or in this case, the sine of our angle would be our imaginary part of our complex number, or our y kind of value, over our r. And so likewise, by taking both sides of this times r, we can see that our b value here, or the imaginary part of our number, is our sine of theta. And then our last relationship that relates theta, at least to a and b, would be this. We say the tangent of theta would be b over a. So what I basically want to do here in this video is kind of using this relationship where we know a in terms of r and theta is r cosine theta, and we know that b in terms of r and theta, b is r cosine theta. What we could do instead then is take our complex number over here on the right, and instead of writing a and b, we'll write this number in terms of some r and some theta. And so that is to say, because we know the a value here, our real part of this number, corresponds to this r cosine theta, and we know that the imaginary part corresponds to this r sine of theta, we could rewrite our number in this fashion here. And I know that this doesn't look very desirable right here yet, but what I want you to understand is this. If we were able to write this number a plus bi instead in this form, then what we would know is what direction we are heading in, theta. We would be clearly told that theta, and we would know precisely how far to walk in that direction. So what I'm going to do here is this. I'm going to take this expression on the right, and I'm going to rewrite it as r cosine of theta. I'm just going to clean it up a little bit, and I'm going to move this I up front. And I'm sorry if that bugs everybody here, but we're going to say I times r sine theta. I just don't want anybody to think that that I is included as part of my angle. So we go ahead and throw that up front as just part of its coefficient. And so looking at this, one thing that you need to know is that they both have a common factor of r. And so it is very traditionally true that we factor out that r in front, and what we get left with is this r times the quantity cosine of theta plus I times the sine of theta. And we're going to give this a name. As a matter of fact, we're going to say that up on top here, this is our standard form of a complex number. Standard form. Often we refer to this as the rectangular form. What we have down here, okay, is still a complex number. So this is a complex number, but in complex number. Let's write number first, huh? Number in polar form. And the reason why it is in polar form is because we are able to determine these two values here, r and theta, from what we have. And so this number in rectangular form, a plus bi, okay, knowing basically that we could rewrite it as this value here, or at least rewrite a and b as r cosine theta and r sine theta, this will always simplify out from rectangular form into this polar form over here on the right. And so you'll always see your polar form of a complex number as being this r times the cosine of theta plus the I sine of theta, each one representing the rectangular coordinate portions of our legs of our triangle here in this right triangle situation. And so here's what we're going to work on essentially. If we're given some number that is in standard form, in rectangular form, a plus bi form, could we rewrite this into polar form is going to be our primary concern here. And the way we're going to do that essentially is that we're just going to borrow from these two definitions right over here that say, well, then your a value would be r cosine theta and your b value would be r sine theta. But we're also going to draw a picture here. But most importantly, we could say that the polar form of a complex number is this r times cosine I sine of theta, or cosine plus I sine of theta. And so some things to mention down here that are really, really important are these. If we want to know what r and cosine are, and r and sine, or sorry, r sine theta, r cosine theta, and how they are related to a and b, we have these two relationships right here. Also, if we know a and b, okay, if we know a and b, we can find r, which is a necessity here, and if we know a and b, we could also find theta right here. And so one thing that I'm going to mention here is this. If a and b are known, then to write in polar form, and right polar form is this r cosine theta plus I sine, take my time here, theta. In this form, we must find both r and theta. And so what that means is we are going to use this quite often, the fact that our absolute value of a complex number, we're going to call that r this time, is the square root of a squared plus b squared. And also that the tangent of our angle, whatever the angle is b over a. And we can see that up here on a relationship. If we look at tangent, we get b over a. So that'll allow us to set up an equation we can solve for our angle there. So worth noting and worth mentioning, we say that the value of r is called the modulus of the complex number z. And so when we refer to the modulus, okay, the modulus here is this value of r. Remember that r is the distance from this complex number back to the 0 point. And so that is also the absolute value of our complex number. So let's make a little note here. We'd say try to spell it properly here. The modulus is the same thing as the absolute value of our complex number. And then our angle here. We're going to assume that our angle will always assume is some positive angle. So it'll leave from 0 here in standard position, but positive angle counterclockwise to the terminal ray of our angle that's going through this point AB. So it'll be some value between 0 and 2 pi, but we're going to refer to that as the argument of our complex number in standard form. And so labeling this up here, we could say that r is a modulus, and theta, we'll pull this over here on the side. This is the argument, and I hope I spelled that correctly there. I did. Okay, cool. So here's what we're going to do in this video. Basically, what I'd like to do is give us a couple of numbers here in rectangular form, in standard form, in a plus bi form. I'll even write this out. We have, a plus bi form here. Looks like a is -2 and b is -2 here. What we want to do is go back and rewrite this so it says z equals r times the cosine of theta. Let me fix that cosine there. Cosine of theta plus the I times the sine of theta. And what I'm going to tell you is basically the two values we are lacking that we need are the values of theta and the value of r. And so let's go ahead and start with this. As a matter of fact, I always want to sketch a picture here. We'll go left 2 and we'll go down 2. It's pretty easy to see that this number here makes this 45, 45 triangle. It's isosceles here. We're going to label these parts. We have -2 and -2. What we want to do in order to write this as a complex number in standard form is find two bits of information. The first one is going to be this theta here that we're heading in. And the second bit of information is going to be this distance r out from the origin. Now, when assessing this situation, I would say it's always usually much easier to find the value of r given a and b because we'll just use Pythagoras to do it. So we can see here that -2 squared plus -2 squared would have to be the value of r squared, or we've said more generally that r is equal to the square root of the sum of these squares here, where these are -2 and 2. So we get the square root of 4 plus 4, which is the square root of 8. And yes, we should always, if we can, simplify this here. So 4 times 2 underneath a radical here, 4 is a perfect square of 2. We get 2 root 2, is the value of our absolute value here, our modulus, okay, or the distance from this point back to the origin. So in terms of writing this number as a polar, in polar form, we can go ahead and write this out front. We say 2 root 2. You could even write the square root of 8. Now, following up with this, we'd say, well, how are we going to find this angle here? Now, remember, r is the square root of a squared plus b squared, but also that the tangent of our angle is equal to b over a. And we were already told b and a in the first place. And so let's go ahead and set up our relationship here. If we knew that the tangent of this is b, which is negative 2, over a, which is negative 2, we get the tangent is 1. So our theta value, or at least our reference angle here, is going to be the tangent inverse of 1. And anybody who knows their tangent inverse of 1, okay, should be able to tell you that, and I'm not going to use my calculator, it's a 45-degree reference angle. And so we say that this right here is 45 degrees if we want to do this in degrees. So if that's 45 degrees, what we can discern about this angle here is that it must be a 225-degree angle. So look at this. Just by drawing our complex number in standard form, we were able to find two things pretty easily: the hypotenuse length, or our modulus, and also this angle just by using a tangent relationship here. And so to write this number as a complex number in standard form, we would write these as 225 degrees. If we're doing this in degrees, 225 degrees. I'm going to write this again down here, but we'd say that we get 2 root 2 times the cosine of 225 degrees plus I times the sine of 225 degrees. Now you might be saying to yourself, I really don't see the benefit to writing a number in this form right here. But what I'd like to tell you about this form right here is that it very clearly tells you, hey, all you got to do is head in a 225 direction and go out about 2 root 2 units from there. You would be at this point here that you formerly said you had to go left 2 and down 2 to get to. And so what I want you to try is this. Pause the video, and I want you to graph this number right here in the complex number plane, but also then rewrite it into polar form. Okay. When you're ready to check out the solution, go ahead and hit play. Looks like in this case, our two values here, a and b. Let's go ahead and start by looking at those. We say a, our real part, is -1. Now our imaginary part is the coefficient of I. And so really that means everything but the I, and we get negative square root of 3 would be this coefficient over here. And so with this, let's go ahead and start by saying, where would this point lie if we drew it in standard form? Now, the square root of 3 here is a little bit bigger than 1, but less than 2. Because it's between the square root of 1 and 4. But if we were to go down the square root of 3, like I said, we go left 1 and down, not quite 2, but more than 1, we'd say it'd be this point right here. And the important bit is that you can draw your picture, because here's what we're going to do. We're just going to label this out: -1, negative root 3. The two things we're after are r and our angle theta. And so more easily this time, let's just use our formulas. We say r, that distance back to the origin, is -1 squared plus negative the square root of 3 squared. When you simplify this is kind of fun. The square root of 3 squared is 3, and even if it's negative, when you square it, it becomes positive. This is going to make this the square root of 4, which means that our r value really is 2. So I'm going to go put that on my sketch over here, r is 2. Now, what I'm going to follow up with is finding this angle. Now, what you have to realize is that you're only finding the reference angle. That is to say, when you set up your tangent relationship, that tangent of theta is actually this angle, this green angle right here. So we would get opposite, which is negative root 3, which is our b value here, over adjacent, which is -1, which is our a value, so b over a. So what we get here is a positive value. And as a matter of fact, anything divided by 1 is just itself. So we get tangent of our angle here is root 3. So we'd say theta is tangent inverse of root 3. And in this case, of course, we know that this here, if we're going to do this, I suppose, in radians, it says express the argument in radians, then we'd say that this comes out to be, our reference angle comes out to be a pi-third, or a 60-degree reference angle. So in terms of what this angle must be up here, we got 1 pi-third, 2 pi-thirds, 3 pi-thirds, 4 pi-thirds, 4 pi-thirds. So what I want to show you is basically this. Once you get r and theta, once you know these things, then the polar form of this number, whoops, not r equals, z equals, is r times the cosine of your argument plus I times the sine of your argument. And this is actually very beneficial, because we could say that, look, we know you're going 2 units, and we know that you're going in a 4 pi-thirds direction. And that would be a way that we could express this in terms of polar coordinates instead of left, right, up, and down. Cheers.